Again, this is Michi. So this is the last presentation. I want to introduce you how NSE works. So this is where we are. So I set a learning goal, understand the principle of NSE operation, and understand the type of soft matter physics or problems that can be solved by NSE. There's some brief example. And understand how to plan a successful NSE experiment. This is also a brief. But mostly, I think I'm repeating what Professor Wagner and Dr. Faraone have said. And why do we need to do this? NSE is a unique spectrometer that applies a unique principle as neutron spectroscopic technique. So this is the only technique that uses polarization of neutrons to see the energy change. As Antonio introduced, we measure the count. Energy exchange, that is one of the parameters you would care. That is a technique, that is normal way to measure these inelastic or quasi-elastic scattering, but neutron spin, we don't do that. That's why we need to introduce this. And second portion, to understand how to apply this technology to your research project. This is the main thing. In the end of this workshop, we want you to propose something that you want to measure with neutron spin. So this is to prepare that. And please stop me anywhere. So outline, so I go back a dynamic range of NSE again, and a conventional Quenz machine, how conventional technique measures, and compare with neutron, principle of neutron spin. And towards the end, a little bit of example, science case, and planning an NSE experiment. Okay, so dynamic range. This is the same as what Antonio showed. So this is Q, length scale D, length scale, and energy or time scale. And neutron scattering techniques cover this range. Among neutron scattering technologies, neutron spin echo covers smallest Q. Smallest Q is largest size, and longest T, or smallest energy exchange. So larger object and slower motion. That is covered by neutron spin echo, among other neutron spectroscopy techniques. And the range, I didn't show it here, but the range is, as Antonio showed, picoseconds up to the best in the world goes to microseconds. That is the range of the time scale we can cover with this technique. So how to measure dynamic neutron scattering? So as Antonio said, we measure energy exchange in the conventional way. Sorry about this poor resolution. But there is a neutron source. From the neutron source, neutron comes in, and there is a monochromator. This defines the energy of neutron. Incident energy, that is defined as EI, or incident wave vector KI. Okay? And he hits the sample and scatters at a certain angle, and comes out with variety of energy, right? Because if there is an inelastic scattering happens, energy exchange happens. And therefore, we can select the energy, the final energy of neutron. In that way, we can see the number of neutrons that count, that is in that specific Q and specific energy. That is the normal way we measure. And this is another way, time of flight. Time of flight. So we know the neutron velocity. Once you know the neutron energy, we can calculate the neutron velocity. So we define neutron energy in the first portion, and we define also time equal to 0. So clock starts at time equal to 0. Neutrons start to run at the finite velocity. So we know when neutron comes to the sample, and we know when neutron comes to the detector. Okay? This is time of flight. How fast are the neutrons? Did you read?
Oh, wow.
The
That's a
handout?
trap. That's a trap.
I don't remember. 600 meters per second? 4 millimeter per microsecond. So you convert 4 millimeter per microsecond. Yeah, typical number. It depends on the energy, of course. Depends on the energy. It's mean to me. Anyway, so if energy exchange happens, time that neutron arrives at the detector change. So from that, we know how much energy was exchanged. So that is a conventional way. So the idea is traditionally define both incident and scattered wave vectors in order to define energy exchange and momentum exchange. And traditional technique use collimators, monocromators, these different devices, choppers, to define those energy of neutron. But NSE does. NSE uses the neutron spin polarization to encode the difference between the Ki and Kf. So at this point, already, so energy of neutron itself doesn't matter, right? To define Ki or Kf. Polarization, that is important. So we completely decoupled energy of neutron, resolution of instrument with respect to the energy of neutron. So we can use poor monochromatization. What this means. So in order to do better energy resolution spectroscopy with conventional technique, you need to define EI and EF very, very precisely, more precisely. Then at a certain point, you will lose the number of neutrons that are useful for your measurement. So at some point, you cannot do better energy resolution spectroscopy. But here, because neutron spin echo uses polarization to measure energy exchange, we can use poor monochromatization. That means the energy distribution of incident neutron is very broad. Typically, we do 10 to 20% wavelength resolution, wavelength distribution, and still we can do highest energy resolution spectrum. So to compare, backscattering, for example, they define the energy of incident energy of neutrons at 0.1% or so. 0.1% versus 10, 20%. So we are using much more number. So to do this, we need to know the neutron precession. What is that? We use a spin degrees of freedom. So neutron has spin up. Oh, yes.
How do you know that the resolution is good or bad?
How do we know the resolution is good or bad? So we know resolution is good because we access the energy, smaller energy exchange region. And so that we can come back with. So for example, backscattering. So incident energy of neutron is about 6 millieV, milli-electron volt, and wavelength resolution is 0.1%. So what you can do with this instrument is the highest energy resolution of 1 microeV or so. Yeah, energy scale is converted to time scale by Fourier transformation, related to each other. So that 1 microeV, that is resolution. And in the case of neutron spin echo, what we are doing is the maximum, the best case, we can do tens of nanoelectron volt. That is the range we can go. But we are using polarization, so we cannot really say the same way that the conventional technique is doing, but I can explain that
The reason I ask this is because the resolution is independent of any sample that you use, and it's completely from an instrument point of view, right?
Yes.
So you have to match the instrument to your problem.
Yeah.
So in a way,
So,
scattering 1 microeV is roughly 1 to 2 nanosecond time scale. If you have anything slower than that, you cannot do it on backscatter. So it's true. What you want is to match the time scale of your sample to the instrumental resolution. But here we are kind of saying, how do you get better and better resolution? How you can push to longer and longer time scales.
Thank you. Now, Anthony is generous.
So let me add to that. I'm sorry to
Yeah,
interrupt. There is a thing that you will never hear in this workshop. But there's a thing I'm telling you as a spin echo instrument scientist. Never start with spin echo. Ever.
Yes, yes.
Right? If in doubt, go to a science machine, do some structure, and based on that, then talk to Michi or any spin echo specialist, and they'll tell you if the sample will work or not for spin echo, if you have any related dynamics unless you have some MD simulations and you already know, oh, I got some relaxation at 10 nanoseconds, then just go for it, right? But since you haven't done any scattering experiment, do not go to spin echo. Spin echo. I tell my students this, spin echo, so if neutron scattering is a company of transportation, spin echo is the limousine. Not everybody gets to ride in the limousine. And by everybody, I mean every sample.
No, I was saying a sports car.
What? It's not true?
Absolutely true.
All right, here we go.
It's a
Sorry.
sports car, like. So, how many neutron spin echo spectrometer in the world? Do you know? Including everything.
That's a good one.
Wide-angle?
Does it
Wide-angle? One wide-angle. And total, handful. Less than 10. Less than 10. That is a sports car. Do you make sports car, very fancy sports car, more than 10? I don't know, but it's like that. So very rare instrument. But that is okay. We know that. We will know that. So anyway, so we use a spin. So either up or down state of neutron exists. And without magnetic field, these are randomly oriented. And with magnetic field, either up or down goes to parallel to the magnetic field. And we can select one state of neutron. So that is polarized neutron. And polarized neutrons, if we have, and that goes to the magnetic field, that has a perpendicular component to neutron spin direction. Then neutron spin starts to rotate. This is a precession, Raman precession. This is very similar concept with the top that is spinning. Along the gravity, it is just spinning. If you have the spin at the top that has some angle to the gravity, then this starts to rotate around the gravity. That same thing, similar thing, happens here. So that is a Raman precession we call. And that Raman precession frequency, that is only depending on B, magnetic field strength. And gamma, that is we call gyromagnetic ratio, that is a constant. So if you change the magnetic field strength, you can change the speed of this rotation, Raman precession. That is what happens when neutron is in the magnetic field. So now, then we can calculate number of precession in a magnetic field. So we shoot in a neutron that has a spin up, and in a magnetic field, and it starts to rotate from here, Raman precession, and it travels in a magnetic field in certain time. Right? So then we can calculate number of precession or precession angle that is proportional to omega L, that's the frequency, times time you are spending in the magnetic field. And we can, this gamma B that is coming from the previous slide, and L by V, this is time. L is the distance, V is the velocity of neutron, so this is time. And now we generalize BL as integral of B, magnetic field. Integral of magnetic field along the neutron trajectory. That we call field integral. And just change to J. This is the generalization. So this is the equation. Finally, we get this is the precession angle. So now we want you to have some exercise. So at NHNR, J range, this is determined by the shape or shape of magnetic field and how much current you can apply. that controls the magnetic field strength. So J, that we have the number around here within range of this. And we can use lambda, wavelengths of neutrons, 8 angstrom. So how many turns of neutrons do you expect in this lambda precision? So equation is here, and parameter you need is here. So can you try to calculate how many turns you are getting? I want you to calculate. It's just to know what we are doing. Yeah. Oh, yeah, it's here. The answer is in the handout, maybe, no? Did anyone get? Yes. What did you get?
On the handout.
Yeah, so it's in the handout. So it is, if it is J, that is 1 millitesla meter, number of precession, that is this precession angle divided by 2 pi. This is radian, so divided by 2 pi, and that comes to 60, our 60. Okay, that is a neutron precession, number of precession, that is 60. But if you go this, highest, then what you get, highest, what you get is 30,000. So that is a range. We have neutrons that is spinning, precessing in a magnetic field. Okay, and you can change the wavelengths, and then you can change the number of turns. This is simple. Now, if we have combination of magnetic fields, so we have magnetic field, and so the precession going here, and we have another magnetic field that is pointing the other direction. The rotating direction goes backwards. And if this distance is the same and magnetic field strength is the same, what happens in the end is number of precession here and number of precession there are the same, but opposite direction. So in total, this phase is 0. That means original spin state is recovered at the end. This is what we do. And if we have sample in between, and elastic scattering happens, what do you expect? What was the elastic scattering?
Change in direction.
Energy loss? No energy loss.
Energy loss and
No
change in
energy
direction.
loss. So velocity, first and second are the same, so the same thing. The original state will recover. Then what if inelastic scattering happens? Now energy is exchanged. So the velocity in the second portion is different from the first portion. So equation-wise, V plus delta V. This does not go back to 0. So neutron spin cannot come back to the original state. So by this, we can calculate how much wavelength or velocity change that is relating to the angle change. Okay, that is a point. And in reality, what we're doing is we are using beam of neutrons, and that has a wavelength or energy distribution. And we need to shoot in everything. But if we see each individual neutron, that has velocity, energy. And if elastic scattering happens, each individual neutrons are following this. So total, in the average, even if it is rotating and look like it is messed up, but it is coming back to the original state in the case of elastic scattering. So let's see the spin echo effect. So we have two magnetic field range, and we shoot in the neutrons with some certain range of velocity, and we see the polarization in the x direction. X direction is up, pointing up. This is the spin, and that is traveling in a magnetic field and coming back. So what I do is we use my spin thing. So this is the neutron spin, pointing up in the beginning, and comes into the magnetic field. And so there are different speed of neutrons. So spending time in the magnetic field is different. So different speed of neutrons is rotating in different ways. Right? So therefore, this fan starts to open, rotating and open. Rotating and open, open and open. And at a certain point, this fan is completely opening and still rotating. So if we follow that polarization in x direction, it is oscillating because of this rotation. And at the same time, fan is opening, therefore we are losing the polarization. And at some point, we completely lose the polarization. But it goes to the backwards. So it goes, in the beginning, it is going like that. Now it's going backwards. So at certain range, it is the same, but at certain point, the faster opening fan is catching up the slower one. Right? And in the end, it comes back to the original. That is what is happening. It's clear? And the case elastic scattering, what is happening? Again, this cannot come back to 0. And in this case, the average of the velocity of neutron, that is kept. Because case elastic scattering probability, energy gain and energy loss, those are the same. So average velocity doesn't change. So pointing the, in the end, the spin direction pointing is up, the same. But the fan cannot completely close because of the energy exchange. That means we are losing some of polarization compared to the original state. So that is what we measure. Okay? And now we need to relate that the angle difference and energy exchange with the sample. So angle difference, we can say this way. V gamma j, V changed, and j, I did the delta j. So magnetic field integral is also slightly different, possible, to generalize. And we can calculate what is a delta phi. On the other hand, delta E, that energy exchange in the scattering viewpoint, we can calculate kinetic energy change. Here I use the lambda, sorry. But we can calculate delta lambda as a function of delta E. Right? These are 1-to-1 relationship. So we can put this in here, and in the end we can get this. So delta T, okay, at the spin echo condition, that delta J equals to 0. Magnetic field integral between first and second are the same. In that case, we get delta T that is proportional to delta E, energy exchange. And we can define, we can rewrite this delta E in frequency, and this coefficient that is take out here, that we call Fourier time. This is a time associated with this energy exchange. Okay? And we can say this is proportional to number of precession. So if your precession, number of precession that is larger, then Fourier time becomes larger. Now another thing, we can calculate the Fourier time. Of course, this is the same thing. It is, the answer is in the handout, but you can really calculate this time. So this gamma, this is the magnetic ratio, and then it's mass of neutrons by H is Planck constant, J is the magnetic field integral, lambda you know, that is the wavelength of neutron. So we can calculate the range of Fourier time we can access, and that is like this. The smallest field integral with 8 angstrom, we can access 10 picoseconds, about 10 picoseconds. And with highest magnetic field, this goes to about 50 nanoseconds. So with the setup we are upgrading, and the old one is already gone. So setup we had with one wavelength of neutrons, we could change the time scale from 10 picoseconds up to 50 nanoseconds. And you can change this with changing wavelengths as well. Because Fourier time goes to lambda cube. If we go lambda 8 angstrom to 15 angstrom, 50 nanoseconds goes to 300 nanoseconds. It's much bigger change of Fourier time compared to J change, that is a linear, lambda change is a cube. So when we do experiment, we set up a wavelengths and shoot neutrons into the spectrometer and change the magnetic field integral to cover this range. If this range is not enough, we change wavelengths and measure different range. So this is spin echo. Most of the portion is measured, explained. That's good. But now we need to measure polarization of neutrons. That is the last portion. So in order to measure polarization of neutrons, we use analyzer. This analyzer is spin analyzer. So one state of neutron spin that can go through. That is a device we have. And detector is here. And you can think of this device is passing through the neutrons which have different angle as a cosine component of that angle. So upstate neutrons go through everything, downstate stops everything. In between, if it is in between, that the cosine portion will come through. Of course, this is not one neutron, you cannot do this, but one neutron either up or down. But the probability that the neutron beam has, that cosine probability that is coming out as a effect of analyzer. So this is a function we have, and this analyzer function is sort of a weight function to the SQE that is happening at the sample. The scattering, if neutron hit the sample, scattering happens. That scattering probability was dynamic structure factor SQ delta E. And we have a filter that is selecting portion of that. So weighting function is applied. And if we calculate this, we have two terms, this SQ delta E, D delta E, and SQ delta E cosine term. What do you think is this? SQ delta E, cosine delta E, D delta E. It's a scattering class. So we know the answer. We have heard this word a lot of times in San Antonio's Fourier transform. So this is a cosine Fourier transform in energy domain. So because it is a cosine Fourier transform in energy domain, that goes to the time domain. And actually, this is a cosine Fourier transform, so this is a real part of SQT that is coming up. So I didn't do anything. So the instrument is doing this Fourier transform. Isn't it handy? And this one, if you put t equal to 0 here, same thing happens here, right? So this is SQ t equal to 0. This is a snapshot, static scattering. That's why we need to stress all static scattering or dynamic scattering before explaining this. So in the end, what we see is static intensity plus dynamic contribution in the spin echo data. And in reality, again, it is we are using beam. So we need to consider the distribution of the incoming neutron wavelengths. But we can see the same thing. Two terms, one is here, the other is here. And second portion, this is the cosine Fourier transform of SQE, weighted by f lambda. First one, this is SQE integrated over with considering the wavelength distribution. So the wavelength distribution smear SQ, that is the first portion. And second portion, we can calculate like this way. So this is the wavelength resolution portion, wavelength distribution portion, and this term is again SQT. So in the end, INSE, what we are measuring by NSE technique is sum of SQ, static scattering, plus SQT, intermediate scattering function, with some function. This is relating to delta J. This is phase difference, right? Field integral difference. So we change field integral difference. If we change this delta J, we can see the echo data like this way. Okay? And at the echo condition, delta J equals 0. We can go back this equation. This equation says SQ plus SQT. These both are 1. So it is SQ that is coming as an average of this intensity. On top of that, we have SQT contribution. That is what Neutron spin echo measure. And I'm also throwing in many information. So this is an instrument. So what we have? Well, we have neutron velocity. Yes. No. Well, we have neutron velocity selector to define the incident energy of neutron. That is 10 to 20% of distribution. And we have neutron polarizer to polarize neutron. So we select one state of neutron. And I have pi/2 flipper in the beginning. So in the beginning, when you polarize neutrons, neutron polarized and the magnetic field, they are parallel with each other. So this, we cannot have a spin precession. So we need to have perpendicular component. Spin needs to go perpendicular. So in order to do that, what is happening is we create 45-degree magnetic field here. And the neutron spin comes in and rotates. And at the time this rotates 90 degrees, this magnetic field is small, just parallel, perpendicular component exists. And then it starts precession. So this pi/2 is the start. And the same thing, pi/2 at the end, this is the stop. So we define the range of precession by pi/2. Yes?
You have a range of velocities coming into your pi-half flipper, and you can only control the magnetic field in the pi-half flipper. How do you know how much you flipped the precession by if you don't know how long it spent with the field?
So that is relating to the efficiency. That's why we cannot use really the white beam. So there is a range of wavelengths distribution we can use because of these devices. And how do I know? That is, in the end, what is happening is we are losing the efficiency of that. That is coming to a loss of resolution. So we try to make good device and try to use with good range. And that is what we have. And we live with it. I think, yeah, but the change is cosine. Change of this neutron spin precession angle is not much, so how to say?
Can I help out? You should know by now. He gave you everything. How does the pi/2 pi/2 flipper works?
rotates it using the Larmor precession, but you don't know the velocity because it's a wide range. So
Yeah,
you don't
but
know how long it spends there.
Yes, how much if you have one given wavelength, how much did the spin turn?
I have some. Then you can
Actually
count.
180 because you turn around an axis of 45, right?
45.
You turn around and you come in like this is the field. You come in like that and you turn 185 degrees, which ends up 90 degrees, but 180 around the axis. Doesn't matter. Take 90 degrees, good enough. Sure. You have 10% wavelength band. So your speed has a 10% spread. So your angle will have 10% spread. That's it.
That makes sense.
And cosine 9 degrees.
Yeah, okay, so it's a negligible spread. Okay, that makes sense.
Thank you. Pi over 2, and we have magnetic field region. Okay. So I explained the spin echo as a magnetic field pointing the opposite direction. But this we cannot do because if we do that, at the center magnetic field is 0, and it's depolarized neutron beam. So we need to make magnetic field in the same direction. But then we cannot do spin echo, right? But we can because if we change the phase, so first one is opening the fan, and if we rotate back, this fan is catching up. Right? That is what I explained. But here we have pi flipper that is in between two magnetic field region, and that is basically what it's doing is pi flip. So this is flipped. And then now this one is going faster, so fan is going to close. So effectively, we can do the same thing. So we use pi flipper, and sample is here, and another magnetic field, and analyzer detector. That is how spin echo works. And we can change delta J, because we want to know where the echo is. We want to change delta J. So to do that, we make these big coils as symmetrical as possible. And we put small coil here in one of the two portions. Then add a little bit of magnetic field. That gives you slight change of the magnetic field integral. And that controls our parameter. So in the end, what we measure is like this. Polarizing intensity is changing depending on this is a phase. So when you change phase, total number of precession that is slightly changing, and we can measure this type of oscillation. And now here, it's an echo condition, fan is closed. And if you keep doing, fan starts to open again. That is what neutron spin echo signal looks like. And this neutron spin echo signal is happening here, up and down measurement. This is to determine the polarization of neutron, and that is relating to the static scattering. So what we can do is we can take out pi over 2 flipper. What happens if you take out pi over 2 flipper?
No, that's not.
That is not happening.
If I'm thinking of this like NMR, I wouldn't have them in the right right plane to measure them at all.
So yeah, so there is no change of the magnetic field spin direction. So always magnetic field and neutron spin are parallel with each other. There's no precession. No precession. It's just going through the neutron in the one state of polarized neutrons going through. And if we have pi flipper here, it flips. So if this guy going through one state this direction, and the neutron comes in this direction, the polarization, okay? And it's nothing happened. The pi flipper is flipping. And if this goes, this doesn't go through. So if sample scatters, which causes the flip, of neutron, if that happens, that portion can go through in this measurement. And we can take out pi group also. Then in this case, it comes in, nothing happens, scattering. If scattering also does not give you any change of the polarization direction, it can go through. If it flips, it cannot go through. So in that way, we can measure this up portion and down portion. And this is relating to the static because we are not having precession. Without precession, we cannot measure dynamics. Again, this is just a recap. We are doing this as a neutron spin echo measurement. And another important thing is coherent and incoherent scatterings. Sorry, neutron spin echo is a bit confusing, but other instrument, if you measure SQ omega dynamic structure factor, what you get is both components of coherent and incoherent, that those are the sum. But spin echo, because we are using the polarized neutrons, we cannot do that. What we are getting is minus 1/3 contribution of the incoherent scattering. Why is this happening? This is because spin incoherent scattering flips neutrons spin direction to the third probability. So 2/3 of neutron spin, that is flipped. So if you think this is all incoherent scattering, okay? Pure incoherent scattering. Neutron spin comes in, and 1/3 that is going through. The other 2/3 that's free. And 1/3 this direction, 1/3 that direction will be canceled with each other because of this spin echo thing. So the leftover is the component from 2/3 that as a contribution as minus 1/3. It is flipped. So phase is inverted. And that is the case, always the case. So coherent and incoherent is mixed like that way. The important thing of this is if you are measuring things in the coherent dominant range, no problem. If you are measuring things in incoherent dominant range, this is also not a problem. You can try, you can say, oh, we ignore the other component. But if you are measuring, if you put 1/3 of coherent, that is equal to, so coherent is equal, the intensity is equal to 1/3 of incoherent, we are losing spin echo signal. They are canceling with each other. So we cannot go that range. So on that range, we cannot do spin echo, but other range we can do. So we can measure incoherent scattering, but with limited capability. Signal will decrease 1/3 to 1/3. Okay. So by using this technique, what kind of science we can do? That is toward the end. Most of the cases, we are saying we measure coherent dynamics. So at the small angle region or some sort of high angle diffraction peak. This is because we want to have more neutron intensity. And what are those? Density fluctuations corresponding to some SANS pattern. If you have SANS, structure exists. Those structural components, if it is not rigid, they will move. Whether that is in your time range or not, that is another question. But if they move, you may be able to measure something. And the range, diffusion, the particle, colloidal particle diffusing within the solution, or shape fluctuation, as Antonio stressed, shape, that if that shape changes with time, those things are what internal dynamics, that is what we want to measure. And the polymer dynamics, chain moving, Laos going out, levitation, those types of motion, and liquid and glassy systems, molecular motions at a high angle, for example. The structure factor peak, liquid molecules moving, what time scale, that is we can measure. And that is relating to structure relaxation and that is relating the friction, so viscosity. And we can do incoherent dynamics in a specific Q range, and that is, again, give us self-dynamics of mostly hydrogen. We can do that, but you need to be careful because signal is 1/3. So it's very weak. So and also, most of the many cases, dynamics measure for incoherent. So some spectrometer covers wide range of Q. So it is more efficient compared to spin echo. Spin echo, we need to define the magnetic field. Therefore, it is not so efficient. So you need to be careful. But at ILL, there is a wide angle spectrometer that can cover incoherent. So we are expecting more incoherent dynamics will be covered using Neutron spin. And some magnetic dynamics will be done, but I don't go here. So this is toward the last. So planning an NSA experiment, which dynamics do you want to identify? That is a question you ask yourself. Here, so you make a clear target while you measure dynamics of what kind of system. Is that time scale, is the dynamics really in your range? The kind of thing you need to think before doing the measurement. Okay? And most probably you would like to know the structure before even think about the dynamics. Without knowing structure, why do you care dynamics? Sometimes yes, but because of the shape, structure, and what types of motion is changing this structure, that kind of thing. So you need to know the structure, I think, and the intensity distribution, because coherent matching is important for spin echo, this coherent, incoherent. So you need to go to a static measurement instrument and determine where is the coherent and where is the level of incoherence. We need to know that. Otherwise, we may not be able to measure even if there is a structure. And estimate time scale of the motion using different types of spectrometer or instrument, DLS, dielectric, NMR, whatever instrument if you can use, try to measure the time scale of motion, and if matches, there is a possibility that NSE can help. And gather enough amount of materials. This is another important thing. We need a lot of samples, except IN15 or ILL, they have much more neutrons, so they can use smaller samples, but here, typically, we're using this size of material, so 1 to 10 milliliter. And 1 to 10 milliliter of, for example, 2 milligram per milliliter of proteins, if you bring, it's hard for us to measure. So you need to ask questions and discuss with the experts. And whatever question you have, we are happy to help because we are here to help you to do experiments. Okay? That is what I have, and this is the learning goal and my response. So understand the principle of NSE, precision to decouple instrument and probe energy resolution. That's why we can do highest energy resolution specters among neutron scattering. And understand the type of soft matter problem, various coherent soft matter dynamics, most of the cases. Understand how to plan successful NSE experiments, better to know static structure before dynamic studies. Okay, that is what I have. Thank you very much.
Please ask question. We still have like 1 more minute. So, Ryan.
You have to worry about multiple scattering.
Multiple scattering.
Yeah. Like we do in static structures. Smearing of time or anything.
Yes. We need to be careful with multiple scattering. For phase work, when you measure it, you measure incoherent scattering because we don't know multiple scattering effect quite well because we first scattering exchange energy. This second scattering how much energy. So that probability is counted as a SQE, right? So we try to avoid that. So in coherent scattering, we know that people are doing transmission higher than 90%, so that 10% scattering, and that is reducing the probability of multiple scattering. And in the coherent scattering case, again, we really don't know how much, what types of effect we are seeing. The smearing in Q direction, that is for sure. Yeah. Smearing in time, that again, SQT, SQ omega. So, but I have never calculated that yet. So I try not to have too much multiple scattering, but in the range that NSE can access, that is relatively low in intensity. So the possibility of multiple scattering, that is not that high. For example, small angle, very, very small angle region, you have very high intensity. There you have more multiple scattering effect. But spin echo, we are going higher Q, so not that much. That is my understanding.
Then we will, yes.
Clarification that this is side. Michi cautioned about not having coherent and incoherent the same spin echo. I recommend not to be not in that case on any other instrument as well, because if you have two dynamic processes taking place at the same time in your spectra, it will be very hard to separate, even if they are summing up themselves. So just want to say that you try to define, project, to prepare your experiment in such a way that you are basically measuring the least amount of variables possible. Otherwise, it is very hard. Just as an aside.
So always we try to go the Q range where for either coherent or incoherent only. Otherwise it's hard.
There's no other question. Please join me to thank Michi.